Here we are, getting to the end. Stats and Mechanics, Year 1, Chapter 10, Question 14. A block of wood, A, mass 0.5 kilos, rests on a rough horizontal ground. Okay, that's different. Attached to string, light and extensible, passes over the pulley, edge of the table. The other end hangs 0.8 kilos, free as shown. Okay, the resistance then. The resistance of motion A from the rough table has a constant magnitude of F. Okay, so we've got a frictional force or something, but we've got F newtons going in this direction. The system is released from rest with the string taut. After release, B descends and a distance of 0. So it goes from here and it drops 0.4 meters, and it does that in 0.5 seconds. Okay, so presumably then we have tension working here, tension working here. The force that's moving this down is going to be 0.8 G. Just for the sake of it, I do have 0.5 G coming down here and a reaction force coming up here, but we're not really concerned about them. Modelling A and B as particles, calculate the acceleration of B. Okay, what do we know? As this comes down, acceleration makes me want to think of Suvat. So let's have a look at what Suvat can tell me. The distance is 0.4, that's good. The initial speed was 0. The final speed I don't know. The acceleration I don't know, but the time I do know. Okay, I've got enough information for Suvat. That's great. What was it? They wanted the acceleration. So looking at that, I want something that does not involve V. Okay, so we're going to use, let's come over a little bit, S equals UT plus a half AT squared. Okay, so plug it all in, 0.4 equals 0 times 0.5. Okay, come across a bit more, plus a half A times 0.5 squared. So that becomes a 0 on there. So 0.4 equals 0.5 squared is a quarter, divided by 2 is an eighth, of A, and so 0.4 times 8 gives me 3.2. So I have an acceleration of 3.2 meters a second is equal to A. Okay. The tension in the string. Well, again, let's work on B. Okay, so let's work on B and let's put together F equals MA for the system of B. I now know this accelerates at 3.2 meters a second minus 2. Okay, so my forces that are against me here, I think what I'm going to do is I'm going to say down is positive and up is negative. So my tension force there is a minus. So I've got 0.8 G, take away my tension, and that will be equal to my mass, which is 0.8 times my acceleration, 3.2. Okay, and now I can just solve that for T. So 0.8 G minus 0.8 times 3.2 is equal to T. Okay, onto the calculator, 0.8 times 9.8 minus 0.8 times 3.2. 5.28 newtons is equal to tension. Yep. Okay, that looks all right. Right then, what's the next bit? The value of F. Oh yeah, we had that resistance force up here. So now that we've done that, we have worked out the tension, 5.28. Okay, so we can put that in, 5.28. Okay, and we can start an F equals ma for the top of the pulley. We also know the acceleration is going to be the same as 3.2. Okay, and for the sake of this one, I will consider that to be positive and that to be negative. So putting together F equals ma, okay, we can say that the force of 5.28, take away the F force on the back, is equal to the mass, 0.5, times 3.2. Okay. So again, 5.28 minus 0.5 of 3.2 is equal to this force F. 5.28 minus 0.5 times 3.2 is 92 over 25, 3.68. 3.68 is equal to F. Okay, so state how you in your calculations how you have used the information that the string is inextendable. Okay, so we've used that because the acceleration is the same. It allows us to know that the acceleration and the tension is the same in the string, but the acceleration mainly. Okay, so the inextensible string means the acceleration will be the same on both sides of the pulley. Okay, there we go. Hope that's all right.